Okay, so we are like maybe about half a day behind the syllabus, right? But I kept up so here. We decided 2 days at the end of it for you. I'm not worried about it. I'm going to finish up 6-7 today and get at least started on 7-1. I anticipate we will cover the last new material on or before Wednesday of next week. And then from there, we'll just kind of review. Okay. Any questions? So, yeah, so, yeah, see, the second functions. And we defined an inner product we talked about this last time. How do you take the inner product of two functions? Well, one way to do it is multiplying and integrating from 0 to 1. And we showed last time this was if these functions are continuous, this does indeed define an inner product. In fact, what you needed the continuity for was really that last one that says the inner product of any function with itself is greater than or equal to 0, and it's equal to 0 if and only a function is equal. So, let me give you an example. Consider P2. This is probably known as degree less than or equal to 2 and 0 polynomial. And a product so let's just kind of make that. So let's apply this inner product to D2. Now, let me ask you this. Can anybody give me a basis? And give me the easiest basis you can think of. I am a simple creature. Remember, a typical element of P2 looks like this. Right? What's the easiest basis you can think of? Yeah. 1x squared. How about that? This is sort of my favorite basis for this, right? Notice that anything in P2 is a linear combination of 1x and x squared, and these are linearly independent. This is basically the analogy of E1, E2, and E3 as a basis of R3. Right? Now, is this an orthogonal basis with this particular inner product? Actually, let me give you kind of a fun. This is an orthogonal basis with respect to some inner products, but not this one. Can anybody see why? not orthogonal with respect to our given inner product. No, it's just for, yes.
Whenever you're writing like one x next door in like vector form, they're gonna be in different rows. They're gonna like, whenever you do the dot product, it's gonna be 0.
Right, so, that's right. Let's look at the inner product of 1 and x. This is the integral 0 to 1 times x. Right? And this is 1/2, which is not 0. So 1 and x, with respect to this inner product, do not sit at right angles. There are other inner products you can come up with that they do, but not in this. Okay. So let's use Gram-Schmidt to refine these to and refine places. And then we'll talk about how to make it with the normal. Okay, well, we just go through the Gram-Schmidt process. So my original basis. So let me record this kind of to help us along. That's my original basis, putting Gram-Schmidt to turn this into an orthogonal. I'm going to call this U1, U2. Now, here's my new basis. B1 is equal to 1. So I'm just going to take that first basis out. Now, let's look at B2. How do I do this? Well, it should be U2. And we subtract off this projection on the first basis. Right? So let's U2 inner product U2 is B1. And of course, what we should get is something that was orthogonal to the original B1. Well, so let's see what we get. U2 is x. U2 B1, well, that's our inner product. So U2 is x and B1 is 1. So and B1, inner product B1 is so let's see what we get with these numbers here. Well, the integral from x 0 to 1, that's 1/2 x squared, so it's half. And the integral of 1 from 0 to 1 is just 1. So I get so 1 and x are not orthogonal, but 1 and x minus half are orthogonal. Finally, we need B3. And now what you have to do is you kind of have to subtract off both of them. So it should be U3. And then we've got to subtract off projections on the other basis of it. So this should be U3 everybody B2. And we've got to get U3 and B1. Like that. Everybody okay so far? All right, let's see what shakes out. Let's see, U3 is x squared. This right here, so you've got to have the inner product of U3, which is x squared, and B2, which is this mess. So it should be x squared times this. So that should be like x cubed minus 1/2 x squared. And we have to take the inner product with B2 with itself. So basically, you get to square this. And now times B2. Yeah, you better keep your eye on this calculation here. Now, we've got to have U3 inner product B1. B1's just 1. So that's going to be the integral from 0 to 1 of x squared dx. And B1, sorry. Now, just so I don't get too out of control of those calculations, let me just take a brief little break here. I've got to figure out what the numbers are here, so I'm going to do this. The interval from 0 to 1 of x cubed minus 1/2 x squared. This is 1/4 x4 minus 1/6 x cubed evaluated from 0 to 1 plus a 4th minus 6, which is 1/12. And let's see what else I got here. I got to figure out this thing here. This is 1/3 x cubed minus 1/2 x squared plus 1.x evaluated to 0 point. So this is a 1/3 minus 1/2 plus 4. So that's going to be -6. 4 is going to be, yeah, so that's going to be 12 as well. So, and of course, I guess in this interval from 0 to 1, x squared dx, 1/3, and then from 0 to 1 dx is 1. So I can now kind of fill in blanks here, and I've got Q3 is equal to x squared. This fraction looks like what? 1/12 over 1/12 times x minus 1/2. And this looks to me like it is 1/3 over 1. And so I guess this comes to x squared minus x plus 1/6. So to answer the question here, my new orthogonal basis one is the space is sort of the normal. Well, I doubt it. What you gotta do is you gotta figure out the length of all these, divide it out, right? And so where's the length? So if I wanted to go a step further and get a normal basis. Let me just do the lengths. I don't bother going through do all this here. The length one is square root of integral from 0 to 1 on the x, which is square root 1. So the length of the first one you're already getting, right? The second one you gotta take the inner product of the cell and take square root of what you get. And I think we already did this one here. One, you got 112. So this should be. Form the square root. Yes.
Why did you not just use square root of x minus 1/2?
Because you have to take the inner product of the cell, right? And so what you're actually doing here is square root x minus 1/2 x minus 1/2. And that involves multiplying these two. If you don't do that, it's possible you come up with a negative under that square root, right? So that's kind of a hint, because you need to get a positive number on that radical. No. And I'm not gonna work with this, the obvious reason, you might try it yourself. Right, I mean, this one, I mean, this isn't intellectually challenging, but it's certainly obnoxious, right? Because you have to multiply this out, get 43 polynomial. Any questions on? Yes.
Oh, never mind. I see what you did.
Oh, okay. Okay, so, let me give you a kind of a final couple of inequalities from the set. So here's some stuff quite familiar from the dot product, although we didn't talk about it so much, but this is true in general for all inner products. Just like Gram-Schmidt, et cetera, pretty much everything follows over. You need this first theorem here. This is called Cauchy. Let B the product space. Remember, don't let that scare you off. That's just a vector space that happens to have an inner product, like we've been doing. And UV vectors in B. Then, if you look at the inner product of UV and then take its absolute value, here, and this is less than or equal to the length of u comes the length. This is a very important inequality, but I can justify it geometrically pretty quickly. And it'll be used on the next one, which is the triangle inequality. So what this says is, if you take the inner product to vector u and v, well, that's going to be a number, and that number could be negative or positive. But this Cauchy-Schwarz is all about size, right? So if you take the inner product of these two vectors, take the absolute value of them, so that's positive, then it's less than or equal to the length of each. This is the big one. Let me justify this. And again, I'm going to use a little bit of geometry to do this. Let's say, now, I can project V on U, correct? This is something that we've done many, many times. And this is this vector here. This piece of U is what I call projection onto U of V. And sometimes I call this V map. Now, size-wise, which is bigger? Which one of these two is the bigger? I wrote the same dang thing. So you should have answered then, because you don't have to. Which one of those two is bigger?
The original.
Agreed. And the reason is because it is the hypotenuse of right triangle. I agree. So it's the old-fashioned Pythagorean theorem. This square plus this square is this square. So this is the daddy max. Do I agree with that? And that's really all you need for Cauchy-Schwarz. Let me apply this. So what was V hat? Well, the way we got V hat was we took projection of V upon U over U and brought it on itself. V hat is this thing, correct? That's exactly what the projection of V on U is. And so this thing right here is just a number. So this is the absolute value of, well, I mean, it's these. This is a number two. What is this number? What is U? U. This thing right here is the length of U squared. Agree? And this piece right here is just the length of U. So I've broken this up into three parts. Absolute value of this. The absolute value of this is just length of U squared, and this is just the length of U. Right. Now notice I can cancel this, right? When I cancel this, of course, I am assuming that the vector U is not of zero length. But let me point out at the beginning that either U and V is of zero length, then this is certainly true. Because, if, for example, means zero length, that means it's zero vector, so it's not zero. So I'm assuming here, and I should have said it earlier, I'm assuming that neither vector B nor U is. And this is plus that equal to the base. Because that's what you all told me over here. That the hypotenuse was the vector. And so if I multiply both sides by that denominator, everybody okay with them?
Vectors for linear.
So the question is, these can only be equal if,
Yeah, well, what's the case for that?
well, so let's see, you would have to have equality, here. Right, so what you would have to do is, yeah, I guess what you need is you would need a projection. You would need B hat to be the same length as this, so yeah. They'd have to be one. It's nice. Good observation. Okay, questions? Let me give you one more. And this again applies to general. One of the general inner products. This next theorem is called the triangle inequality. And this is kind of an old hat, you know. You all know the old thing from geometry that if you have, if you take any triangle, the length of any side is no more than the lengths of the other two sides added up. Right? So it's called triangle inequality. Let B the inner product space again. And B and U vectors and vectors. Then look at so if you look at the vector U and the vector B, right? So you can think of this sort of geometrically this way. And this is why it's called triangle inequality, because you can think of U plus B must be greater than, or U plus B should be no more than the length of U plus B. Let me show this concretely using what we know about inner products here. The length of U plus B squared, it's almost up there. The length of U plus B squared is just the inner product of U plus B. Right? Let me break this up a little bit. This is U because I can split this up over the first term. But now I can take each of these two little pieces and split them up. So for example, this one is U U plus U B. And this right here is B U plus B. Now, by the way, what's another name for enterprise view itself? This one is just the length of U squared, right? And this one is the length of B squared. And these two are the same, right? Because inner product in order doesn't matter, right? So this is 2. Now notice that this is less than or equal to. Because this is a positive number, or at least 0, same with this. This can be positive or negative. And so it's certainly less than or equal to if I replace this by times with that, right? Because this is positive, this is maybe negative. Right? And so this is continuing. Uh-oh, how do I make that step? I'm saying this guy is smaller than or equal to this. So in fact, we repeat that one here. This thing, which was the last thing on the board over there, is less than or equal. This one's right there. Why? Because of these two, this one is less than or equal to this by the Cauchy-Schwarz equality. So this thing is smaller than this one, and this is equal to so. Let me summarize from where we started. We have the length of U plus B squared is less than or equal to the length of U plus the length of U squared. Both these quantities inside the square are positive, and so there's the triangle. Okay. Any questions on that? So these are two important things to remember, the Cauchy-Schwarz and the triangle inequality. So those in mind. Okay, any questions? I'm gonna start talking about. So we're gonna basically cover two more sections, this being one of them. Now, it turns out that symmetric matrices, it just sounds like it's pretty, right? Oh, it's symmetric. But actually, they exhibit an amazing number of. So let me just break up something. 1, 2, 3, 4, 5, 6, minus 1, 4, 12. Okay, let me take my notes here. Let me ask some random production. Is this diagonal? Can you diagonalize this matrix? I've got no idea. What would I have to do to figure it out? Does anybody remember? We've got one big theorem. How can you tell if a matrix is diagonalized? What's it mean? Oh, right. You have to have real eigenvectors, but can you? There's something about the eigenvectors that tell you.
Isn't it, if it has n linearly independent eigenvectors?
That is exactly right. If you have, in this case, n is 3. If you have 3 linearly independent eigenvectors, it's diagonalized, right? And so what that means is, so for example, if this turns out to have 3 different real eigenvalues, then that means it must have 3 linearly independent eigenvectors. Right? Now, okay, that's a great theorem, right? If you have an n by n matrix, if it's got n linearly independent eigenvector, you're good to go. It's diagonalized. What about this one? I don't know. I mean, just looking at it now, I don't even know if it's got 3 real eigenvalues. Right? This may have a pair of complex conjugate, and then there's no way I can do it. Right? I don't even know without doing some kind of crack with the eigenvalue, right? And figuring some polynomial out. The point I'm making is, if you just stare at a matrix, you can't really tell if the thing's diagonalized. I can't even tell if it's got all real eigenvalues just from looking at it in general. However, symmetric matrices circumvent this problem. Let me recall. Call a matrix A. Of course, to be symmetric, you'll see from the definition that's the square. What does it mean to be symmetric? Anybody remember?
There is a matrix, a vertical matrix, you multiply by to cut out some.
I think you might be thinking of something else. So, yes.
Would it just be that like the location of like ij in the matrix equals ji?
The matrix is actually equal to its own transpose. So in general, for a 3 by 3 matrix, here's what it means to be symmetric. The diagonal entries can be anything I want, but once I make a choice here, it has to be the same here. If I choose this B, B has to be here. This matrix is symmetric because across you've got symmetry across the diagonal. That is, it equals some transpose. Or for example, 4 by 4. this is A, B, C, this has to be A, B, C. And if this is X and Y, this has to be X and Y. And if this is gamma, this has to be gamma. That's what a symmetric matrix is. Let me give you a spoiler, right? The spoiler will problem me. Symmetric matrices have all real eigenvalues. That is not obvious, right? But whenever you encounter a symmetric matrix, a symmetric real matrix, it will have all real eigenvalues. And not only that, symmetric matrices are always diagonalizable. In fact, they're diagonalizable on steroids. They are orthogonally diagonalizable, which I haven't defined yet, but I'm going to tell you what it means. So it's even stronger than being diagonalized. Let me kind of start with an example. Let's do a complication here. I'm going to do this. One's a warm up, and one's kind of a thing. So symmetric matrices don't always have nice eigenvalues polynomials. So let's start with this example here. 0, 1, minus 1, 1, 0, minus 1, and minus 1. Notice this is a symmetric matrix, right? I want to diagonalize. Of course, I'm making a lot of claims you can do it, but it will turn out that you can. So the first thing I'm going to do is I'm going to go through the process. Let's find the eigenvalues and the eigenvectors. So this is first the determinant of A minus lambda I, which is the determinant of minus lambda 1 minus 1, 1 minus lambda minus 1, minus 1, minus 1, lambda. And this turns out to be, let's see, this would be minus lambda times the piece here in the lower right. That's lambda squared minus 1. Minus 1 times the determinant of this matrix here was piece right here, so that's going to be minus lambda minus 1. And then finally, minus 1 times the determinant of this matrix down here on the lower left. That's going to be minus 1 minus lambda. Well, let's see what happens here. Okay, so this is minus lambda lambda squared minus 1. Well, it's minus lambda cubed plus lambda plus lambda plus 1 plus 1 plus lambda. And this becomes minus lambda cubed and I guess.
This is the sign of the second term of it, they used to be positive, so just no, it's no.
Yeah. Honestly, but. So is everybody with me? So here's the tough part, right? So. Actually, the roots of this are the same as the roots of the negative ones. So I'm gonna do this. Anybody know the cubic formula? Yeah, it's hard. Actually. There's actually a quartic formula. Anybody know the fifth degree formula? There is actually. It can't be done in general, so, but we can try Hail Mary. Anybody see a solution for this? A root of this? Something you can plug in? Let me give you, how many of you know the rational root test? You ever heard of this? Is kind of an important thing. Any rational root, now, this isn't guaranteed to have any rational roots. We might be totally those. And it has three real roots that are not rational at all. But any rational root must be a divisor of the constant term divided by a divisor of the leading term, which in this case is one time. So your only possibility for rational numbers are plus or minus one, plus or minus. That's it. If none of those work, you're out of luck. Any of those work? Yeah. Two does work. Because 2 cubed is a minus a 0. So this is lambda cubed minus 2 lambda squared. So lambda. Right. Oh wait. And this should be. Let's see, to the root of this, right? So this is lambda cubed minus 2 lambda squared. And this should be. Oh, yes, I didn't see these. What are the other two? We actually got one. See how that one factors? This is now, under normal circumstances, so we've got 3 eigenvalues. And the 3 eigenvalues I get here are and I write -1 twice to emphasize the fact that this has got multiplicity too. Now, see if y'all can figure out that. We'll finish this example next time. See if you guys can figure out the eigenvectors for this. Let me ask you this. Just from what we know so far, does this choice of eigenvalues, does this guarantee us that it's diagonalizable? I know that all the eigenvalues are real, but what could go wrong? Yeah.
Eigenspace for the eigenvalue -1.
That is correct.
One basically.
An eigenvector here and an eigenvector for -1 would be linearly independent. The problem is the eigenspace corresponding to the multiplicity 2 minus 1 might only have one linearly independent eigenvector. Check this matrix. We'll be able to get back to the second one. I promise you, for -1, you will find 2 linearly independent eigenvectors. Okay, any questions? All right, well, think about, doing the math club, don't forget you've got a quiz to the 5, and the next one will appear this evening after that one's done. Other than that, you guys have a good weekend, we'll see you on Monday.